This video is going to be questions 4 and 5 in your acid-base notes. Two types of problems here. Okay, one's going to be where I give you pH. Okay, so you have a known pH of a weak acid, and I ask you to find Ka, and then just the opposite. I'll give you Ka and ask you to figure out what the pH of the acid would be. Remember, the bigger the Ka, bigger the K value, the more you have of these two things. The more you have H+, the stronger the acid. The more the acid moves to the right, dissociates, the stronger the acid. So again, two types of problems. Give you pH, or I could give you percent dissociation, something a little bit different, and you find Ka, or I give you the Ka value and the concentration of a weak acid, and you tell me what the pH of that acid would be when it's dissolved in water. So two types of problems here. Your first problem here has to do with an acid called nicotinic acid. And the formula of nicotinic acid is right there. So here's a dissociation of that weak acid. Again, it's a two-sided arrow, meaning not very many of these molecules dissociate. A majority of them stay together as a molecule. Equals H plus the conjugate base of that weak acid. Or a lot of times I won't write that out. I'll write it like this. I'll write HNic dissolved in water produces H plus ions plus the conjugate base. I'll just put it as Nic negative. So a lot of times I won't write all of that out. For this problem, I will do that. Remember, H plus is synonymous with H3O, the hydronium ion. So H plus is the same thing as H3O positive. Those are the same two things. So I'm going to erase this. Here's our K expression. So K would be concentration of H plus ions times the concentration of the conjugate base all over the concentration of our acid. So let me simple little ice table. We have 0.1 mole dissolved in 1 liter of water, and it tells us the pH is 2.92 at that point in time. So once it's dissolved in there. So if we simple the ice table and say, okay, initial change, equilibrium, this is 0.1 molar, none of that, initially to start with. Once this dissolves, a little bit of it dissociates, and the pH is found to be 2.92. So remember, if we know the pH equals negative log of the concentration of H+. So if we know the pH, we can find the concentration of H+ ions. And whatever the concentration of H+ ions are, would be the same as this concentration. How many moles of this produced would be moles of that produced. So we can do 2.92 equals negative log concentration of H+. So you got to hit a second function, log of negative 2.92. When you do that, you get a concentration of 0.0012. So the concentration of H plus is 0.0012 molar. Again, that's using the pH to get concentration of H plus. So at equilibrium, this is 0.0012 molar. This is 0.0012 molar. So this would have gone, that means these went up. Both of these went up by 0.0012 molar. This would have gone down by 0.0012 molar. So 0.1 minus that would be 0.0988 molar. 0.0988 molar. So at equilibrium, we have this much H plus, this much of the conjugate base, and there. So we can plug into our K expression, 0.0012, 0.0012, and that there. So K equals 0.0012 times 0.0012, or that squared over 0.0988. And our Ka value is 1.46 times 10 to the negative fifth. Pretty small K value, meaning not a lot of this dissociates. But look at how much did. This was 0.1 molar to start with. Only this much dissociated. A whole bunch of it stayed together as a molecule, still pretty concentrated as a molecule, only a small amount dissociated. So again, the problem is giving you the concentration of a weak acid and the pH, asking you to find Ka. Percent dissociation. Okay, percent dissociation is what percentage of this splits apart into ions. There's 10% split apart, there's 1% split apart. What percentage of these molecules are splitting apart into ions? Obviously, the more that split apart into ions, the stronger this acid and the bigger the Ka value would be. The less it split apart, the lower the percent dissociation, and the weaker the acid. So this is asking the percent dissociation for this. So the percent dissociation of this acid would be, there's 0.0012 molar out of an original 0.1 molar. So that many moles dissociated out of 0.1 we had originally. So you're always trying to figure out how many moles dissociated out of what we had originally. Obviously it's a percent, so we're going to go times 100 and get a percent. In this case, it is 1.2% dissociation. In other words, only 1.2% of those molecules, only 1.2% of these molecules split apart into ions. The other 98.8% stay together. So fairly weak acid. So that was the first problem. That was finding Ka with a known pH.